In this lecture we will discuss Perkin condensation. Condensation reaction between aromatic aldehyde and aliphatic acid anhydride, having at least 2 alpha hydrogens in the presence of a base, is known as Perkin reaction. In this reaction, an anion of an acid anhydride adds to an aromatic aldehyde to produce β-aryl alpha-beta unsaturated acid. In order to prevent side reactions, the base that is used to make the anion of the anhydride is usually the sodium or potassium salt of the acid corresponding to the anhydride. The reaction is carried out by heating the aldehyde with excess of acid anhydride, which acts as solvent, containing carboxylate salt at more than 165 degrees Celsius. As an example, consider this reaction of benzaldehyde with acetic anhydride in the presence of corresponding basic salt, that is sodium salt of acetic acid. The reaction is subjected to heating of about 180 degrees Celsius. The product obtained is cinnamic acid. In fact, this reaction was well suited for the efficient synthesis of cinnamic acids, as investigated by W.H. Perkin. Besides simple aromatic aldehydes, there are vinylogs, heterocyclic aldehydes, and even phthalic anhydride, as the carbonyl component, gives this reaction. The accepted mechanism of the Perkin reaction is as follows. First, the enolate of anhydride is formed using the basic sodium salt of acetate anion. The basic acetate anion abstracts an alpha proton from anhydride to form an enolate of anhydride and acetic acid. This enolate then gives a nucleophilic addition reaction with aromatic aldehyde to form an alkoxide intermediate. Then intramolecular acyl substitution takes place. This happens by intramolecular attack of the alkoxide ion upon the anhydride end of the molecule. This forms a cyclic ring, which opens on anhydride side to form carboxylate ion, called beta-acyloxy derivative. This carboxylate ion is then acetylated by anhydride in this way. That means an acetyl group is added on carboxylate oxygen, and the basic acetate ion is regenerated from anhydride. The basic acetate ion then induces E2 reaction, so that acetate anion is eliminated, resulting in the formation of anhydride product. This anhydride product is then hydrolyzed to form β-aryl alpha-beta unsaturated acid, cinnamic acid in this case. Notice that this part comes from aldehyde, whereas this part comes from anhydride. Meta-directing groups in the aromatic ring, of course, promotes the reaction, as these make aldehyde more electron deficient. When anhydride with only one alpha hydrogen is used, no dehydration is possible, and an aldol-type product is isolated. Now let us do some questions based on Perkin reaction. In the first case, the product of this reaction between this aromatic aldehyde with excess acetic anhydride in the presence of basic salt of acetic acid can be easily written like this. The red part comes from aldehyde, whereas the blue part from anhydride. In the second case, phthalic anhydride is reacted with acetic anhydride in the presence of basic salt of acetic acid and is subjected to heating. The acetic anhydride, as usual, acts as enolate part and phthalic anhydride acts as carbonyl part. The product can be easily written like this. Again, red part comes from phthalic anhydride, and blue part from acetic anhydride. In the third case also, the presence of double bond doesn't affect the reaction, and product can be written easily, with red part from aldehyde, and blue part from anhydride. The fourth case is interesting. The first step is usual Perkin reaction between aldehyde and anhydride, so that product is β-aryl alpha beta unsaturated acid. Then intramolecular condensation between acid and orthohydroxyl group forms the coumarin via dehydration.